So, I would like to introduce the band. Close the event. Close the event. Huh?
We still have time till
No.
9.
Close the event. No. Close the event. Okay, thank you everyone. Let me introduce the band. That's Siddhartha on the acoustic guitar. That's Yashwanta on bass guitar. That's Anil on the keyboards. This is Snehita on the drums. That is Venkatesh, Vidya. This is Vidya Sagar, and I am Gautam. We are on vocals. We would like to thank our faculty coordinator, Dr. G. Varka ma'am, and Dr. Y. Padmasai ma'am. And we'd also like to thank Chenakeshwar Rao sir and T.S. Rao sir, ECA CCA chairman. And we would also like to thank Dr. C.D. Naidu sir, our principal. And finally, we would like to thank the IEEE management for giving us this opportunity to perform. We would like to thank Ramesh sir, transport in charge. And we would like to thank Pawan Kumar for the sounds. Thank you so much.
మరిచిరు త్యాగరాజు నీ కృతినే పలికెను మరిచిరు త్యాగరాజు నీ కృతినే పలికెను మరియ మహా నగరే కలకత్తా పురి నమ ಹೋಗಿಲೆ ಹೌರಾಬಾರದಿ నేతాజీ పుట్టిన చోట గీతాంజలి పూసిన చోట పాడనా తెలుగులో ఆహంస పాడిన పాటే ఆనందుడు చూపిన బాట సాగనా పదుగురు పరుగు తీసింది పట్నం బ్రతుకుతో వేయి పందం కడకు చేరాలి గమ్యం కదలిపోరా ఒకరితో ఒకరికి ముఖ పరిచయములు దొరకని క్షణములు బతుకుల గజిబిజి ఉరుకుల పరుగులలో యమానగరి కలకత్తా ಹೋಗಿಲೆ ಹೌರಾಬಾರದಿ ಚಿರು ತ್ಯಾಗರಾಜು ನೀ ಕೃತಿನೇ ಪಲಿತೆನು ಮರಿಚಿರು ತ್ಯಾಗರಾಜು ನೀ ಕೃತಿನೇ ಪಲಿತೆನು ಮರಿಯ ಮಹಾ ನಗರೇ ಕಲಕತ್ತಾ ಪುರಿ ನಮ ಹೋಗಿಲೆ ಹೌರಾಬಾರದಿ ಥ್ಯಾಂಕ್ ಯು
ఇంకో సాంగ్ పాడచ్చు
గౌతమ్ 10 వరకు మనదే 10 వరకు ఎవరన్నా బాయ్స్ ఎవరన్నా పాడచ్చు ఎవరన్నా డోంట్ బ్రేక్ ద ఈవెంట్ బ్రేక్ చేయకండి ఈవెంట్ వెళ్ళండి
చెక్
Tanveer sir join होगा नहीं चलता
చెక్
after Tanveer sir join you can start
మహాగణపతిం మహాగణపతిం మనసా స్మరామి 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 वसिष्ठवामदेवादिवन्दितमहागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दितमहागणपतिं मनसा स्मरामि महागणपतिम् महादेवसुतं महादेवसुतं गुरुगुहानुतं महादेवसुतं गुरुगुहानुतं वामदेवं प्रकाशं शान्तं वामदेवं प्रकाशं शान्तं महाकाव्यनाटकादिप्रियम् महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकाप्रियं महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकाप्रियं महागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दितमहागणपतिं मनसा स्मरामि महागणपतिम्
చెక్ చేద్దాం. ఇది ఏ నెంబర్ ఇచ్చారు? ఏ నెంబర్ ఇచ్చారు? దీనికి ఉంటుంది, దీని నుంచి దానికి వెళ్తుంది. త్రీ త్రీ
Three on. Three is prohibition.
Hello, can anyone speak?
Huh?
Hello, please talk for a while. Can anyone talk for a while? Hello? Hello, Bhargav?
Hello, madam.
Yeah, can you hear me?
Yes, madam, it's audible.
Thank you. Hello. Hello. Good morning, Tanveer sir.
Yes, good morning.
Good morning, sir. Sir, shall we start?
Yeah, please, I'm ready.
Yes. Good morning, one and all. I welcome you all to the second day of IEEE SPS event on latest trends in machine learning for signal processing applications. So we have exciting speakers today. To start with, we have with us Dr. M. Tanveer, Associate Professor and Ramanujan Fellow at the Discipline of Mathematics, IIT Indore. Dr. M. Tanveer is a Ramanujan Fellow at the Discipline of Mathematics of the Indian Institute of Technology, Indore, since July 2016. Prior to that, he spent 1 year as a postdoctoral research fellow at the Rolls-Royce NTU Corporate Lab of the Nanyang Technological University, Singapore. He received the PhD degree in computer science from Jawaharlal Nehru University, New Delhi, and MPhil degree in mathematics from Aligarh Muslim University. His research interests include support vector machines, optimization, applications to Alzheimer's disease and dementia, biomedical signal processing, and fixed point theory and applications. Dr. Tanveer is the recipient of 2016 Ramanujan Fellowship, which is one of the most prestigious awards of India. He is the reviewer of American Mathematical Society USA and a member of editorial review board of Applied Intelligence Springer series, that is International Journal of Artificial Intelligence, Neural Network and Complex Problem Solving Technologies. So we have, sir, for the title, Optimization of Machine Learning Techniques for Signal Processing and Case Studies. So let's start the session with all the energy and zeal. I welcome you all, sir. Thank you.
So, may I share the screen?
Yes, sir.
No. So, please confirm if the
Yes, sir. We can see the screen as well as hear you.
okay.
Thank you, sir.
So, very good morning, everyone. So, first of all, I would like to thank Professor Padma Sai and the whole organizing team for the kind invitation uh, to deliver some talk, especially I'm not sure about the title of this talk as mentioned by Professor Padma Sai. So essentially, I'm going to cover here the optimization algorithms, especially for machine learning and application to signal processing, like some applications for the EEG based and MRI based.
Yes.
So it will cover that title, but since I had decided to fix the title here, EEG or MRI based universal support vector machines. So I hope that the participants have some basic understanding of support vector machines, general classification or regression problems. So even though I'm trying to explain a bit more about SVM initially for 10 minutes, what is SVM and how geometrically we look at it and how mathematically we formulate it. And then we'll move for another algorithm, especially for EG based classification and MRI based classification using advanced SVM algorithm. So this is the overall idea of this algorithm. Some content I just mentioned here, that support vector machines and support vector machine based recursive feature elimination universum data. We'll discuss the advantages of it, and some purpose algorithm, and then applications to Alzheimer disease data. And based on some results, we'll discuss. And then we'll move for the EEG signal classification using universum SVM, and then some advanced algorithm in this direction, and some more results, and then we'll conclude this talk. So this is the overall idea of this talk. So let me first discuss about support vector machines. So support vector machine is one of the most powerful tool for classification problem. Initially for classification, it was developed by Wapnick and co-workers in 1995. And in the same year, it was also extended for the regression problem. So, and nowadays, if you look at it, it has been applied almost all the possible directions. Means the people having background electrical engineering, computer science, physics, math, biological sciences, almost all background people are using for their work. So for either classification or regression or clustering, so whatever they want, so they can use it. So, but since it was developed in 1995, so a lot of improvement from the last 27 years. So whatever theoretical issues or numerical issues were there. So authors from the last 27 years means a lot of advanced algorithm have been developed, especially for uh, the more accurate algorithm, more fast algorithm, more robust algorithm, more sparse algorithm with diverse domains. So we'll discuss in a few directions today. So the basic idea of original SVM, we are talking about first classification problem. So the basic idea is to find a best hyperplane, a best line between positive and negative samples. So let me give a very simple example here. Uh, Suppose we have a data points. Uh, you can see here we have two different data points, and you can see that we draw a line in the middle. You can see we have this line. Okay, so we draw some line here to classify this data. So we can see that it's clearly classified these two samples, two kinds of samples. So, but you can see that I draw another line, and I can again see that these data is again properly, perfectly separable. So the question is, you can find out another line is also nicely separable. So, and you can draw n number of lines to classify this kind of data. So the idea is that there are many lines, and we see that the line is perfectly separate these two different class of data. So now the question is, which line is best to classify this data? So SVM help us. The first property is the concept of maximization or maximum margin. So we are going to discuss that point here. Yeah, there could be a possibility that if there is a misclassification, means we draw a line and data point of the right class is wrongly moved to another class, so we penalize those data points. We'll discuss those. So initially we were discussing that we have two class of data points. So suppose we have this is +1 and -1. positive and negative samples, and we have now n number of lines. So the first question is that which line is best, which line is optimal line. So the first concept is maximizing the margin. So what is margin? Is nothing but the distance between positive and negative samples, such that this distance is maximized. This one between positive and negative samples. For example, this is positive samples and this is negative samples. So this distance means if we draw a line in the middle and that distance from both the classes is maximized, so this is called maximizing this margin, maximum margin. And the data point which lie on this supporting hyperplane is called support vectors. So support vectors are those vectors which help us to decide the decision hyperplane. That is the middle line. Middle line is exactly in the middle of these two, this one and this one. Okay, so the middle one is the optimal hyperplane. Okay, so now we can explain this mathematically. So how to say mathematically? Suppose we have w dot x plus b. Let me see that here. Suppose I say w dot x plus b. This is greater than or equal to 1. And this is w dot x plus b less than or equal to minus 1. Means the data point which is below this is are these points, w dot x plus b less than or equal to minus 1, and the data point which is above this is w dot x plus b greater than or equal to 1. It means that data point which lie on the supporting hyperplanes w dot x plus b equal to 1 and above 1, right? So and here this is same equal to minus 1 or below this minus 1. So we have, and at the same time we have to maximize this margin. We had to maximize this margin, and margin is, if you we explain here, this margin is a distance between these two supporting hyperplanes. So this is, if you simplify this one, and this is maximizing the margin is nothing but we have 2 upon norm of W. So essentially we have to maximize this margin. So equivalently we can write minimize norm of W by 2. Or equivalently we can write norm of W square by 2. So now we reformulate the original SVM algorithm that let me write here, that minimize norm of W square by 2 and subject to the constraint. If I merge these two equations, so essentially I can write this is yi w dot xb greater than or equal to 1, and here y is nothing but plus minus 1. If it is positive samples, so then this will be w dot x plus b greater than or equal to 1. If it is minus 1, y equal to minus 1, then it will be like this. So we merge it in a single constraint. So it will be yi w dot x plus b greater than or equal to 1. So this is one of the simplest way of designing this concept, maximizing the margin using SVM concept. So we are minimizing this weights W subject to these constraints. Any doubt so far? If any, yes, please let me know. We can discuss, because I did nothing so far. I just explained how we have two class of data, and we want to classify it. What will be the best line, best optimal, best hyperplane to classify this kind of data? So even if you just see an example of a classroom, boys and girls are sitting in a classroom, and boys are sitting one side and girls are sitting on another side. And this is the same example. I had taken two different kind of dots. So what would be the best separating line? So the best separating line will be if we draw a line between boys and girls in such a way that the distance between boys and girls are maximized. So that would be the best separation, right? So, and the middle line is called the decision hyperplane or optimal hyperplane. Okay. And we design the same concept mathematically, that we just have considered with the definition of hyperplane, and we say that data point which is below this equations, if we have below this one, so we had w dot x plus b greater than or equal to plus 1. So we just explain this as maximizing this margin subject to these two constraints. The data point should lie below this and above this. Okay. So finally, we design this algorithm of SVM. So this is the first SVM algorithm for classification problem. So this is without any misclassification. Simplest one, simplest SVM algorithm. Okay. So now we can discuss soft margin also. Means when there is a misclassification, means while finding out the optimal hyperplane or decision hyperplane or best hyperplane between these two classes, so there could be a possibility while drawing this line that data point of one class can move to another class. Like you can see that we have this data point. It was essentially should be this direction, but it was wrongly classified. Okay. So then what we do here, that we penalize with some xi, suppose some xi1, and some here, this is also wrongly classified. This is some xi2, and so on. There could be n number of misclassification. So what we do, we add in the objective function, like we are writing this minimize norm of w square by 2. So either you write the norm of w square by 2, or means this is equivalently you can write okay. So this is same. So in the objective function, we add all those classification errors, whatever it is coming, we sum up, and with this C parameter that control the overfitting. So that parameter that while solving this problem using some coding like MATLAB or Python, so we had to be careful in taking the range of the C to find the best value of C for better classification, rather than just putting any number. Okay. So far we discussed these two concept that were the first SVM algorithm is this one, and this when we have misclassification error, so we have this one. Okay. So now moving ahead, while I'll discuss in detail after a few slides. So I just give the overview essentially here that what happens when we are solving SVM algorithm. So what we observe that in the dual formulation, those who are aware of, otherwise we'll discuss here today, that while solving this problem, what we observe that the data point appear in the form of dot product. So this is important, not for the here we are dealing with the linear case. So essentially it will help us to understand the concept when we are dealing with a non-linear case. When we are working in the high dimensional space, it will help. Just keep in mind this point that while solving the problem of linear case, and when we are going to relate the same with the non-linear case. Okay. Now I'm moving to the non-linear case here. So what happens? Let me just explain with this first example. You can see that here we have two different kinds of dots, blue dots and red dots, and we want to classify this data. So you can see it's nicely classified. There is no problem. So because we have red data points on one side and blue data points on the right hand side, so there is no issue. We can directly draw a line in the middle and it's work nicely, no problem. But what happens if we have the data point of this kind of second option? So then we cannot do actually and linearly. The problem is, so we cannot draw like this. We can classify blue and red data point like this. So in a single line, linearly we cannot classify. So what to do? Just an intuition that since in real line we cannot do that, but we can see here in this figure what we do, that we map means if we have like this and we just map fx equal to fx square. Okay, means we just move from 1D to 2D. So what happens, you know, the this fx equal to x square map. Okay, so what happens when we just put these data points here? So what happens, these data points will move up. When the data points will move up, so we can see that we are able to draw a line so that these data points are linearly classified in red and blue dots. Okay, this is just an intuition. So but we can draw, means whatever the difficult problem is coming to us, we can do this. So with this intuition, you can see that if we have very complex data, you can see that we have a circle inside the red data points and outside blue data points. So what to do in this case? Because if we go from 1D to 2D 1 to 2D. So this is not there because already in 2D. So what to do? So now another concept of SVM is coming into the picture. So first we have discussed one nice concept, maximizing the margin. Now the second we are discussing the kernel trick. So how this concept is coming? So what we are doing that we map this input data. We map this input data with some phi function. I mean, we map this from Rn to Rm. And here m is strictly greater than n. So we map the input data in some high dimensional space where these data points are linearly separable in some dimension. So now the question is coming in which dimension? Do we need to know? So the answer will come. What happens? Let me first explain this. When we were dealing a linear case, linear SVM, and I ask you to keep in mind that the data points appear in the form of dot product, like xi transpose xj, like this. Okay. So what happens here? We are explaining that if every data point is mapped into higher dimensional space via some transformation, so the dot product becomes like this: phi transpose phi. Okay. So there are different kind of kernel functions available in the literature that can be used later wherever the problem is coming to us. So what happens while solving the problem for the case of nonlinear? So what happens in place of x transpose x, we see that this coming. This is nothing but phi transpose phi. Maybe some xi, xj you can just put. So phi transpose phi. So what happens, what we observe that while dealing with a nonlinear case, so and solving the dual, what we observe that the data points appear, nonlinear data appear in the form of inner product. So inner product is nothing but is a number. Okay. So essentially what happens when we're dealing with the nonlinear case, we are dealing with a high dimensional space, but essentially we are working in linearly. I hope that you understand the concept that we are dealing the data in the high dimensional space, but we are solving the problem linearly because the whatever we are getting in the solution, we are getting this in the form of phi transpose phi. Phi transpose phi is nothing but it's a simple number, inner product. Okay. So you can see here that as just an overview that SVM locates separating hyperplane in the feature space and classify points in that space. It doesn't need to represent the space explicitly. That I was explaining that we have this phi and we are mapping from Rn to Rm and where m is strictly greater than n. So here in the case of nonlinear, we do not need to know about the nature of phi, but we just need to calculate phi transpose phi. And phi transpose phi is nothing but is a number, and this is essentially a kernel function. like if I write here, let me, sorry. So essentially what happens, so suppose if I write x1, x2, okay, like x1, x2, okay. So it doesn't need to represent the space. That is why explicitly we do not need to know, because while solving this, we are simply defining by a kernel function k. And here kernel function play the role of dot product in the feature space. Any doubt so far? Okay, so if no doubt, then we can go ahead. Okay, so far I was discussing more on geometrical point of view to explain that how SVM works. Let me bit explain mathematically at how this theoretically works. Something I have written directly that the solution. So how to do that? So I can little bit here motivate with this formulation now. So as I mentioned that SVM look for the separating hyperplane W transpose X plus B equal to 0 between positive and negative samples. We have two supporting hyperplane between positive samples and negative samples, and we want to find out a decision hyperplane, optimal hyperplane. So with the concept of maximizing the margin between positive and negative samples. So equivalently, we have seen that here this regularization term half norm of W square, and data point which lie on the planes are termed as support vectors. So this is another nice picture, pictorial representation, that the distance between this positive and negative, this supporting hyperplane is 2 upon norm of W, and the middle one is optimal hyperplane. And we have this the data points here represented, they are support vectors. Okay, so now let us discuss here this formulation. I'll discuss only this one. So I hope that rest you can easily do. I'll try to explain this one. So it's quite easy that we have seen that how we are getting the dual formulation. So we have the objective function that half norm of W square plus capital C, C is a parameter, and summation xi are slack variable, and subject to the constraints that data point should lie above or on class 1 and below or less than -1 with this xi. Okay, now since it's an optimization problem, okay, how to solve an optimization problem? So, and it's a constraint optimization problem. So let me first give the basic understanding of an optimization problem. Here, suppose we want to minimize a function subject to the constraint gx equal to 0. Then the necessary condition for x naught to be a solution, that the partial order derivative fx plus alpha times gx at x equal to x naught should be 0 and gx equal to 0. And here alpha is a Lagrangian multiplier. So suppose if we have multiple constraints and we have the similar kind of constant, that is g1x equal to 0, g2x equal to 0. So then essentially in this case the necessary condition will be the similar kind of, we just sum up all the constraints like partial order derivative fx plus summation alpha I gix at x equal to x naught is 0 and gix also equal to 0. Okay, so since our problem is constraint optimization, that is the inequality. So what to do in the case of inequality? Suppose we have this kind of problem. Minimization fx subject to the constant gix less than equal to 0. So then there must exist alpha I such that x not satisfied this one. And when we are talking about this optimization problem, so then fx plus alpha I gix is known as the Lagrangian function. So while solving it, we take the partial order derivative, equate to 0, then we solve all this. Okay, so since we were solving this problem, it is our idea. So first we write the Lagrangian function. Okay, means suppose I write this is fx, and this is we can rewrite in the form of gix less than equal to 0 or greater than or equal to 0. In any form we can write. Okay, either means you can take another side, less than or greater than. Okay, so this is the idea. So first we can write the Lagrangian function like fx plus summation alpha I gix. So this is what we have done, that we have the Lagrangian function, this one, and now here alpha and beta are Lagrangian multipliers. We take the partial order derivative, equate to 0, solve the problem, then as easy directly you can find out in a one or two steps we are able to get this one, and we see that that the data points are appear in the form of dot product xi transpose xi. This is what we were doing. And in the case of nonlinear case, so essentially if you go exactly in the same manner, we have taken the nonlinear SVM and we solve the same problem, and we observe that in the dual formulation it appears in the form of this phi transpose phi. Okay, any problem so far? Any doubt? Anyone? Okay, I think there is no doubt so far. It's good. So now I'm moving to my another talk like this. So now I'm going to discuss the concept of recursive feature elimination with the case of SVM. Okay, so in general, the feature selection play an important role in the classification of data. So since we are going to discuss for AD and Alzheimer disease and EEG signal classification. So usually if I talk about Alzheimer disease data, so many researchers used voxel-based morphometry, analysis of MRI images. So in Alzheimer disease, there is atrophy in gray matter and white matter tissues that lead to increased uh, cerebrospinal.
Hello, sir. Am I audible?
Yes, yes, please.
Sorry to disturb, sir. I have one doubt. May I ask?
Yeah, please go ahead.
Sir, I am a PhD research scholar. I am doing the several experimentations. So what I found that when if we take different feature vectors, different combinations of features, then with the same classifier, that is with SVM, sometimes with linear kernel I get the better result. Sometimes with RBF kernel I get the better results. So means how to interpret, sir, this means I know that means through literature survey I understood this, that this is also like means that depends on data, but how do we interpret, means how while understanding what should be my understanding from that experiment that I am not able to write it down, interpretation. So can you highlight on this?
Actually, that's a difficult question. So what happens? You have given the even one clue that the choosing a kernel is depend on the data. So sometimes the same data for the linear case the performance is good, but for the non-linear case is not good. But
Yes, sir.
but what we observe that most of the time that the linear data is not performing well, but for the non-linear cases is performing well in general in the literature. And we also have seen in the literature that if you are choosing this RBF kernel, Gaussian kernel, so usually in the literature that the performance on RBF kernel or Gaussian kernel, same, is the performance is better. So, but this is not the universally true that it will always happen. So another question here in the literature that the choosing a kernel, a specific kernel for a particular data is still a difficult problem, and it's difficult to say that this particular kernel is perfect only this data. So now people already developed, if you have done this multiple kernel theory in SVM. So please go through that, and there are other way so that you can improve the overall performance. If you take your kernel in the weighted kernel or ensembling of kernels, suppose you have 10 kernel functions, okay, like exponential or maybe RPF or polynomial kernel and so on. So you can ensemble you take the different kind of combinations. This is also another area of research. So, but if you ensemble of these weighted kernel, these kernel functions, and then you apply, then the overall performance is going to be improved. This is very, very clear from the ensembling theory in machine learning. So the overall performance will improve.
Yes.
So, but in
Yes.
general, difficult to say. Yes, बताइए.
Sir, the as you said, the assigning weights to different features, is this the same like as in a ranking algorithm?
I'm not talking about. I'm talking about assigning of weights in the kernel function.
Oh, yes,
Suppose
I understood.
you have 10 kernel function. So I'm not going to that particular this data. So I'm just discussing, since you have pointed out about the kernel. Okay, so if you are suppose if you are taking weighted kernel, suppose kernel 1, kernel 2, kernel 3. Okay, so what you do, you just take a w1 k1 plus w2 k2 plus w3 k3. Okay, and weighted approach, many weighted approach, you use it that. Okay, and then choose it as a kernel. Okay, so then use it. So then the overall performance will improve.
Yes, sir. I understood. Thank you, sir.
Okay, so here, in which institution you are doing PhD?
Sir, I am from Pune University.
Okay, okay, great. Thanks. So now I'm moving to another related direction using the concept of recursive feature elimination. So, and we are the first that use this concept for EEG signal classification using universum concept. Uh, and we also apply this concept for the Alzheimer's disease. And we already know that support vector machine has been widely used in machine learning techniques for classification of epilepsy disease and Alzheimer's disease and other diseases. And support vector machine classify data based on the maximum margin principle, and it utilizes the structural risk minimization principle for regularization while reducing the empirical risk. So essentially, it leads to a better generalization performance with less overfitting of the data. So also the optimization problem of SVM gives a globally optimal solution in comparison to techniques like artificial neural network that suffer from the problem of local minima. So in 2002, we are discussing this paper. You can see Guyon et al. This is gene selection for cancer classification using SVM. So they propose a feature selection method for cancer classification. Okay, that term as support vector machine based recursive feature elimination, SVM RFE. Okay, so what happens? In SVM RFE, the feature weights are assigned on the basis of SVM classification, and the features are selected from the data set in a recursive manner using weights from SVM classifier. And it's a very popular feature selection technique, and it has been applied in several applications. So to reduce the computation cost of SVM RFE, so another concept recently introduced, twin support vector machine based RFE. So we'll discuss about twin SVM also in this lecture, that when we are dealing with a twin SVM, so it is faster than SVM theoretically and numerically. So just to reduce the computation cost. Okay, so and this SVM RFE also applied in multi-class classification, and many directions already applied due to its advantages. So what happens to encode the meaningful information about the distribution of data? So we are going to use universum samples in the RFE process. So what happens? So this is the original SVM RFE algorithm that we just train SVM classifier using the weights taken. You see here, we compute the rank, and this is already available in the literature. So essentially, we are going to discuss the universum samples, universum concept, to encode the meaningful information about the distribution of data. So we use universum samples in RFE process. So essentially, the universum samples are in the same domain as the problem at hand, and hence provide a prior information about the distribution of data. So universum samples do not belong to the data set, but are related to the classification problem. You can see that. So we have the data points. This is positive class, this is blue, and red another date, another class. And here green data here in the middle is a universum data. Okay, so universum samples do not belong to the data set but are related to the classification problem. For example, we will see in the EG classification, I think we'll discuss later that what we see in the EG signal classification, we have seizure-free data samples used as a universum classification when we are dealing with for the classification of healthy and seizure. And here, what we observe in the literature that when we are dealing with the universum concept with the SVM, so universum SVM shows better generalization performance when compared with the SVM. And it has been applied in many applications. So the idea of universum is to choose the complexity of the model as per the data distribution. So in order to improve this SVM RFE, what we were discussing, so we also recently proposed universum RFE algorithm for classification problems. So this is the original SVM RFE, universum SVM concept, and we are going to introduce RFE here. So in this case, what happens, we have the separate and also here this additional in the objective function, and we have extra constraints. Due to that, this complexity is going to increase. And while solving the dual formulation in the same manner, so it is applicable for the nonlinear case that the data points appear in the dual formulation or in the form of inner product. Okay. So this is the concept that we have developed in 2020. So what happens, this SVM RFE algorithm, it lacks the knowledge about the distribution of data. So in the recursive process, the SVM classifier eliminate features on the basis of local information about the distribution, about the data. So in order to incorporate knowledge about the data distribution, we use universum samples. We'll see in the next figure. Sorry, I already explained. Yeah, this figure here. Okay. So now, so what happens? The resulting universum-based algorithm uses this prior information about the data distribution and the recursive elimination of features, leading to better feature selection. So now, if you are interested to implement this algorithm, so please go through the GitHub link of it is available on my homepage. So please find out that. So most of the recent codes are available on the GitHub. So if you are really interested to use this concept, so the codes are publicly available in my GitHub repository. Please go there and you can apply. Okay, so this is just we while solving, we have the universum data points for the feature selections, and we just exactly, and then we just rank, and finally for the output we just rank the list. Okay, now moving that, I'm going to discuss another concept, Alzheimer disease. So you know that Alzheimer disease is one of the most common cause of death in today's world, and MRI provides an efficient and non-invasive approach for the diagnosis of Alzheimer disease. So efficient feature extraction technique are required for accurate classification of MRI images. So we motivate with the concept of this SVM RFE, and we develop a novel feature selection technique to incorporate the prior information about the data distribution in this process, feature elimination process. So and whatever for the case of implementation, we have used the publicly available data, ADNI, ADNI data, and the main objective of this ADNI is to analyze the effectiveness of neuroimaging techniques like MRI, PET, and other biological markers and clinical neuropsychological tests to estimate the onset of Alzheimer's disease from the state of MCI. So for more information, please go through the website of this ADNI. So you will see. Now, moving ahead, while in the numerical experiments, you will see that several performance measures like accuracy, sensitivity, specificity, F1 score have used in the numerical experiments. So if any of you are interested, because the problem in Indian data that here in the doctors, especially AIMS, NBRC, or those brain institutions, so they are directly not sharing the data. So we have seen the issue in India. But if you look at like Australia, Germany, or US, so the whole data is publicly available, and researchers are directly helping them to give the efficient algorithm for their patients. But major issue with Indian scientists, especially medical doctors. So we as a AI experts, we are ready to help the doctors, but there is a distance between scientists and doctors not sharing the data issue. Okay. So you know that currently more than 50 million people are affected by dementia, and by 2050 it may expected 152 million people are affected. So diagnosis of Alzheimer's disease is a seriously formidable task that requires a lot of expertise and a thorough examination of patient data. And examination of such a vast amount of data is prone to human error. And the application of machine learning in detection of Alzheimer's disease has shown very promising results and has been very active topic of research in the last decade. So different feature extraction techniques have been utilized by the researchers to classify Alzheimer's disease, this Alzheimer's data using machine learning methods. So you can look at those data which is publicly available like ADNI and AIBL data, OASIS data, So they are already publicly public their data. So in these data, mainly feature selection techniques play a very important role in the classification of data. So in case of Alzheimer's disease classification, many researchers have used voxel-based morphometry analysis of MRI images. So please look at that in detail. And support vector machine also play very important role in machine learning for classification of Alzheimer's disease and other diseases also. So here we have used the concept of universal SVM for using approach recursive feature elimination for the classification of Alzheimer's disease. So you can see here that the performance of our proposed algorithm universal SVM RFE with the baseline SVM RFE algorithm for healthy and Alzheimer's disease. So it's a very simplest case. So we usually get better accuracy here. So you can see when we discuss with the baseline and the proposed one. So proposed is performing very well. And here also CN versus means healthy versus Alzheimer's disease. You can see that the proposed idea is performing very well throughout. So one can look at this algorithm for their implementation. Yeah, when we go for another features, so here we were discussing about especially VBM features. Okay, so here we just discussed the accuracy in the left side and the right hand side. We discussed F1 score using VBM features. So this is just an illustration of reduced GM voxel obtained after a feature elimination process. And the left side is a proposed algorithm, and the right hand side is a baseline algorithm on CN versus AD. Okay. So these are some more experiments here. We just show the accuracy and F1 score for the CN versus MCI. And also we compare the feature elimination process based on the classification accuracy of the baseline algorithm in A, and B is the proposed algorithm. Means the first row is the baseline and the second row is the proposed algorithm. You can see that for the gray matter features, the proposed algorithm is performing very well throughout. So here we are discussing EEG signal classification using universal SVM approach. So we already discussed the universal SVM concept, and we can see here this EEG signal classification. So we have three different kind of state: healthy, control, interictal state, and ictal states. So usually our contribution is not towards the data, neither for AD nor for AG. So our main contributions towards the development of algorithms. So, and this data also we have taken is publicly available. This is we have given this reference, and this data set contains 5 sets like Z, O, N, F, and S. Each set contains 100 single channel EEG signals sampled at a sample rate 173.61 Hertz and of 23.6 second duration. So these informations are available on this paper, which is publicly available, and the set Z and O are surface EEG recording of 5 healthy volunteers with eyes open and closed respectively. The sets N and F are recording of 5 patients in the interictal street and the region of recording in the hippocampal formation of the opposite hemisphere of the brain in N and the epileptogenic zone in F. And the set S is for the ictal street consisting of seizure recording from all the recording sites exhibiting ictal activity. And the mode of EEG recording is intracranial for N, F, and S. So how we did that? So let me just discuss the proposed approach here. So the first step is we just choose a feature extraction technique and extract the features from training data consisting of healthy and seizure data points. Then extract the features from the universal points which are taken from the seizure free. Then we reduce the dimension using PCA or CDR and then train the model using training data with the universal and then test the model using steps 2 and 3. And then use the classifier. Okay, so I just shared here a few experiments, so it's publicly available. So please go through this paper. You can see it's highly cited 2018 paper. So please go through this paper. And this is the first approach actually using the universal SVM for EEG. Okay. So you can see that the performance wise is better on this EEG data. And also you can see here the performance is better when we go for like ICA DB4 and the rest. Okay. In general, the performance is better for the proposed algorithm. And here also you can see that when we compare the proposed algorithm with all the baseline, you can see that the proposed algorithm is outperformed this one in the red star. Okay, so now this is just a representation of epsilon insensitive tube in universum tune SVM. So here the green data points are the universum data points, and we have the class +1 and -1. So we just take the distance of epsilon tube here to just represent. So this is our idea algorithm. We have epsilon tube, this one. The second constant is for universum here also, and in the objective function we have the extra, this term E transpose psi. Then we just go for the dual in the same manner, and then we solve W B for plus and minus classes. And okay, now we can discuss now the next algorithm, least square twin SVM. I'm not sure whether you are very much clear the concept of twin SVM. So let me first discuss the concept of twin SVM. So essentially what happens in the case of twin SVM is a binary SVM classifier that determine two non-parallel planes by solving two SVM related problems, each of which is smaller than the conventional SVM. Okay. So what happens is a new non-parallel plane classifier, which is called a twin support vector machine for classification. So the idea is to generate two non-parallel planes such that each plane is closer to one of the two classes and as far as possible from the other. Okay, so in the least square sense, we just what we are doing in the original twin SVM, we just replace with the one norm with the two norm of this eta 1 and eta 2, and then we just replace inequality with the equality in the least square. Then we solve this problem. Okay, so since it's a old algorithm, so and a lot of improvement has been done. So what we have done here essentially that in this problem we use the concept of universum data to give the more meaningful information and better performance. We already have seen that universum approach giving better performance. So we just use that concept in the of universum data in the least square twin SVM. So you can see that, and further we use the concept of universum data in least square twin SVM with the concept of parametric margin. So, and we also apply it in Alzheimer's disease data. It's publicly available. So please go through this paper for more details. So essentially here, this is alternative formulation when we as compared to with universum least square twin SVM. And here the solution is nothing but we are simply solving system of linear equations, which is more efficient and fast algorithm. Okay. So we already have taken this data set from AD, Alzheimer's AD&I. So please go through the AD&I website or OASIS website, or maybe if you just Google it, you will find out those details. Okay. So any doubt so far, just let me know. From anyone. I think no question. Okay, good to see. Okay, so we can see here some results based on the new concept of universum for least square parametric margin. So we compare all the baseline algorithm and we see the performance, especially average rank. The last one is the purpose algorithm, and you can see that the average rank is best among all the baseline algorithm. So one can use this algorithm for their task. And now we have used the statistical test in general that if we have multiple data and multiple algorithms, then it's important to go for the statistical analysis, because to check whether your algorithm is statistically significant based on the accuracy. So it's very important to understand that. So we also have done this NAMNI post hoc test and pairwise significant difference between the proposed algorithm and the baseline algorithm. So you can see that the proposed algorithm is significantly different than all the baseline algorithm. That clearly show how the proposed idea is efficient. Now further we check, because there are parameters here, we check the sensitiveness of these parameters. So we also have seen here that selection of parameter is very important and sensitive for accuracy. When you move slightly move up or down the value of C, so then the accuracy is changed. So means we have to be very careful in the selection of these parameters. So while implementing the algorithm, we had taken the range of this C and mu, and then we use this tenfold or fivefold cross validation, and we have to choose the best parameters from using that. Okay. So in Alzheimer's disease data, AD and I, so we have seen that CN versus AD means a healthy control and the Alzheimer's disease. So the most difficult one is MCI versus AD. This is very difficult to classify because mild cognitive impairment and Alzheimer's disease, because it's very close. If you look at the MRI of MCI and AD, is very, very close. So difficult to classify these two MRI. So, but we see that in this difficult case, our proposed idea is performing very well. So you can see that for the case of TNSVM, this is 61, and the second highest is our top. Second highest 61, and our is 64. It's a huge difference. So, okay. Now I'm going to conclude my lecture here. That here we have proposed a universum-based technique for feature selection. It provides an improvement over SVM RFE algorithm by giving prior information about the distribution of data. And on the basis of our analysis on Alzheimer's disease, proposed universum SVM RFE has performed better than SVM RFE in most of the cases for classification of CN, MCI, and AD. So moreover, we presented an approach of using voxel-based morphometry on training and testing phase separately. And on the basis of experimental results, it can be stated that the proposed universum-based approach gives better performance for the classification of EEG signals as compared to the baseline algorithms. And the proposed algorithm of selection of universum points have proved to be promising approach for the classification of healthy and EEG signals, seizure EEG signals. And the effect of outlier on the universum is reduced by using the universum from the EEG dataset. And the distribution of intellectual signal provides prior information about the distribution of healthy and seizure signal, and also lies in between the two classes. And a novel universum-based algorithm is proposed in this work, termed as universum least square twin parametric margin. And this formulation, the optimization of this problem, it involves a parametric model that essentially solves simple system of linear equations. So in future, one can apply by selecting universum sample from different classes of the classification problem. And the proposed approach performing well for the classification of AD, showing its applicability on real world biomedical application. One can use it for another biomedical applications. Okay. A few research projects are going on. I have mentioned only a few ones. Rest, please go through my homepage. Few projects are running based on AI, ML, and healthcare. So I just acknowledge my all previous funding agencies. So now with this, I invite you to join IEEE Computational Intelligence Society Summer School on Deep Learning and Computational Intelligence Theory and Applications. So I'm going to announce very soon online this detail, and hopefully I can share with the chair so that she can share with all of you. So tentative this 18 to 22 October. So please join us. And I'm also the journal chair of ICONIP 2022. This is a top ranked conference we're organizing here in India after 18 years. So please join us. I think the submission deadline is over, but you can join us as a participant also. I think it's over from my side. So thank you so much for your attention. So now in the next few minutes, I'll take a few questions from the audience. So any questions from the audience here?
Hello, sir.
Yes, yes.
Thank you, sir. Thank you for clear and crisp information about support vector machine, be it linear, non-linear, and just telling us that it's a constrained optimization problem and giving us the mathematical background around it, and also introducing us to the concept of universum based feature selection method. It was an interesting session, sir. Thank you, sir. Thank you for your time.
Okay. Okay, thank you so much.
Thank you, sir.
So I can close this?
Yes, sir. Yes, sir.
Okay, thanks.
Thank you, sir. Thank you, sir. All the participants are requested to join the next session by 11:30. Please join by next session for the next session by 11:30.